Hello, my name is Natalie. We're going to be talking about X-ray physics, so week 3. So I'm going to start off talking about the anode heel effect, very important, and we'll use it to our advantage in our chiropractic offices one day. So starting off, I just drew a little picture of we already know that this is going to be the cathode and the anode. So we'll have, first of all, you have to make sure that the waves they go from alternating current to direct current. That happens before any of the electrons are going into the tube. So that's the first thing. And then, so from the cathode, the electrons will boil off via thermo-ionic emission, remember keyword. They'll travel across, going over to the anode. Some will go deeper into the anode and won't go anywhere. They'll end up being completely absorbed by the tungsten, which is where the focal spot would be right here. So the tungsten is rotating, is actually like a thicker, dense area, which will absorb the X-rays, which is why over here on the anode side, since it's absorbing those X-rays, they're less intense. So you want to make sure, which we'll later talk about the placement of the X-rays whenever you're or placement of the beam on the human being. So this way, then the X-rays will come down perpendicular, which will give you a sharper image. So the electrons will shoot across, hit off the anode, hit at a focal spot, and the focal spot is rotating very quickly, as we know, because we want to make sure that the anode side is dissipating heat the entire time, or it could actually ruin the product. So some of the X-rays will end up going straight down, some will shoot off to the side, some will go all the way to the opposite side, shooting over closer to the cathode side, which is known as a radiographically dense area, which means it'll show up more black on the screen. So when you're looking at the film will be more black on the cathode end, and then lighter and more sharp on the anode end. And that's due to the fact that the X-rays are actually making a perpendicular angle when they're coming out, when the X-rays are coming out, which makes it more sharp. And there's actually more X-rays absorbed because of the tungsten being so dense on the anode side. So keep that in mind. So there's another way where the heel effect changes the sharpness detail is whenever you're changing the angle of the anode. If there's a larger angle of the anode versus the smaller angle of the anode, there will be a smaller effective focal spot on the smaller one, and a larger effective focal spot on the larger one, which wouldn't give you as sharp of an image as what the smaller anode side. So we're more focused on wanting to have a smaller effective focal spot, because the smaller the focal spot is, the more sharp the image will be. And as you can see, I drew a little geometric comparison. With the larger one, the actual focal spot is just slightly bigger than what the smaller one is, but as it reflects off the anode to produce the X-ray, it'll make a larger focal spot, thus it'll be not as sharp versus the smaller one, which will be a lot more sharp. Okay, so where is the anode heel effect most evident? It's most evident in the types of films that we'll be looking at as chiropractors one day, which are in the 14-inch by 17-inch large films, and a smaller short image distance, which is what SID stands for, in case you forgot, source image distance. But you can think short because you want it, we were usually using only 40 inches for the distance away. So chiropractors usually use 40, and other areas they might use a larger source image distance. Now, in order to figure out where the anode is located, if you just don't have any idea where it is, there's 3 ways of determining that. One way is obviously looking at the plus or minus side. The plus side is going to be the anode side. The second way is trying to listen for the rotation of the rotator, and so it'll make a noise, or you can feel for vibrations. And a third way would be to just look for the wires. The wires will be sticking out from the anode side. So those are 3 ways of locating the anode. So moving over, using the anode effect to your advantage as a chiropractor when you're taking films, you always want to place the cathode end towards the thicker side of the body and place the anode end towards the thinner side of the body, because remember over here, the anode side is less intense. So if you have a smaller proportion, areas of the body, you want the less intense side towards the smaller tissue area. So keep that in mind. So when we're looking at films, the AP thoracic, which some of these don't make sense, with AP thoracics, you're taking it from the front view, versus, so if you're from up here, so T1 to T12, from up here to the bottom, right in the front, usually the breast tissue is going to produce, you're going to have more breast tissue towards the top. So that's why you'd want the anode side at the top. With the lateral lumbar, you also want the anode side on the top. Lateral thoracic side, which can be a little bit confusing, but and the only way I was able to reason through why it's at the bottom is because typically the rib cage will be bigger and have more tissue there versus where you would have at the top. So even though the ADP thoracic is at the top, the lateral thoracic anode is going to be on the bottom end. ADP pelvis will be at the top end, and you can kind of compare that to your butt. Your butt has more tissue there, so you don't want that. You want the cathode and the more dense area, anode on the top. And the 14 by 36 inch full spine, top of the body is typically a lot smaller than what the bottom side or the bottom end is, so you want that to be on the top as well. And she also mentioned the 72 inch SID, so source image distance of with the lateral cervical view, and that doesn't really matter, but if you were to actually do it, you probably want it on the top, but it doesn't matter. All right, so we also talked about the units, which only way of really getting through this, I think, is just to memorize them. So let's do this and we can get through this first exam. So the units are, I just like to think of air exposure. When you're thinking about the air exposure unit, that's the Roentgen, I might be saying it wrong, but they use that, they just use a capital R for the abbreviation for that. Now that's the way we use it here in America, but everywhere else they call that coulombs per kilogram. So if you want, those are used interchangeably, but because as Mrs. Sandy Everidge says, we're different in America, we like to use R for air exposure. For the absorbed dose, we use RAD, whereas everybody else uses gray, and you can abbreviate that by GY. Occupational exposure, we use REM, and everyone else, they say Sievert, or Sievert, however you want to say that. And just so you know, typically we were able to take up, or able to have up to a 5,000 milli REM, which remember that's occupational exposure, per year. But typically for the people that are utilizing the radiographic x-rays and everything, they only have about 100 milli REMs exposure per year. So that's really not bad. We have a lot of giveaway there. So those are the key numbers. 5,000 milli REM per year is the maximum amount that we can handle, but we typically only end up getting 100 milli REM per year exposure. And then the other word she mentioned, she didn't really make a big deal out of it, was curie, which are the radioactive toxins we use here in America, and the AKA for that is becquerel. I don't think we need to worry about that though, but just so you know, it's in the notes somewhere, but don't have to worry about that too much. And as for that, I think that completes everything for X-ray physics week 3.